Afternoon, grade 12s. My name is Ulonwabo and I am the Physics and Life Science tutor at MYC, which is short for Mbegwene Youth Center. We usually host classes on Saturdays for grade 10s and 11s. But since it's COVID, we are doing a special COVID lessons through video. So today I'm going to be focusing on physical sciences. And the specific subject in physical sciences today that I'm going to be speaking about is rates of reactions, as you can see on the board. Now this is for the grade 12s, of course. In order to understand rates of reactions, you have to understand that there are certain things that influence the rate of reaction. In case you didn't know, rate of reaction refers to the speed at which a reaction occurs. Right? So it's how fast or how slow a reaction occurs. And what are the factors that influence the speed of a particular reaction? Right? And how do we explain how these reactions occur? Because it's reactions between chemicals. One chemical reacts with another chemical in a certain way and gives rise to a different product. So it's two reactants coming in different, reacting to form a different product. So today we're going to be talking about what are the factors or initially how these reactions occur, what is needed for these reactions to occur, and what are the factors that influence these reactions. Okay, so how do we explain how these reactions occur? We explain how these reactions occur with something called collision theory. Collision theory. Okay. So what does collision theory say? Collision theory says that in order for a reaction to occur, there have to be sufficient collisions, right? Collisions at specific energies. Right. So this theory says that in order for two chemicals to react, right, they need to collide. Not only do they need to collide, they need to collide at specific energies. And if they don't collide at these specific energies, and the energies are not the same for certain chemical reactions. For some chemical reactions, the energy is higher. For some chemical reactions, the energy is lower. But so we need to keep these two things in mind. Sufficient collisions. So the molecules literally need to collide with each other. Secondly, these molecules have to collide at a certain energy in order for a reaction to occur. Right? So, now let's get into the factors that influence the rate of a reaction. And we are going to explain these factors in terms of collision theory. Right? So factor number one, temperature. So this literally refers to the temperature of the solution. So of solution. Right? So how hot or cold it is. Secondly, we're going to refer to the concentration. Right? Thirdly, we are going to refer to the volume. Or not volume, it is volume, but let's say pressure. Right? Pressure. Okay? Then catalyst. Finally, nature of reactants. I'm going to explain all of these individually. Reactants, okay. Furthermore, we have surface area. Okay, so these are the 1, 2, 3, 4, 5, 6 factors that influence how fast certain reactions occur. So we have temperature, the heat of the solution itself, and then we have the concentration of the solution itself. Now, if you don't know what concentration is how tightly packed are the reactants in a specific area. So let's take this area A, right? And we say it's 5 decimeters cubed, right? So it's in a specific area. And then we take the same amount of reactants, we put it in half the area. So a smaller area, but exactly the same amount of material. So this would then have a higher concentration than that one. So it's how much chemical there is in a given volume. That is the concentration of the solution, or the reactants, or the products. All right. And then we're dealing with pressure. Now pressure, we only take pressure with regards to gases. Right? Gases. Right? So we only look at pressure with regards to gases. In terms of solids and liquids, we don't look at pressure. Now pressure has to do with, okay, we have gas, let's say, in a chamber or in a balloon. Same amount of gas, let's say 5 grams of gas. 5 grams of gas, right? It has a certain pressure, let's say 5 kilopascal, 5 kPa, right? And then what we do is we take the same amount of gas, right? And we make the volume of the container much smaller. So what we do is we're increasing the area in which the gas is contained, which means that there's a higher pressure because there's less space for the gas to move around than in this space, right? And what I'm going to do after this is that I'm going to explain each of these in terms of collision theory. So remember what we said, collision theory is how we explain how these reactions occur. So it has to be able to explain why temperature is a factor that influences the rates of reactions, why the concentration, and all the others that follow, right? And then this is a catalyst, right? Now, what's a catalyst? A catalyst is an agent that you add to the solution that speeds up the reaction or slows it down actually without changing the reaction itself. So let's say you have hydrogen and you have oxygen, right? And then they form, we don't write it like that, we write it like this, then they form H2O, okay? Now let's say this particular reaction happens at a certain rate. Let's say it takes 2 minutes for this reaction to happen. Now what a catalyst would do, you'd say, all right, I want this reaction to happen faster for whatever reason. I want this reaction to happen faster. So what you would do is you said H plus O plus whatever catalyst you choose, right, will still give you H2O. But now let's say it's going to take 1 minute. Right? So if you notice here, we added the catalyst, and the catalyst is a chemical, so it's a chemical like these two. You added the catalyst, but it did not change the product. The product remains exactly the same. Right? So that's what a catalyst does, and I'll go more into detail about catalysts because there's not one kind of catalyst, there are various kinds of catalysts that you can talk about. Right. And then we talk about the nature of reactants. Now, when you're speaking about the nature of a reactant, You're speaking about its properties, the properties of a reactant itself. So hydrogen has certain properties. Oxygen has certain properties. Maybe we know this for a fact that hydrogen is more flammable than oxygen. That means in certain chemical reactions it's going to behave very differently from oxygen because of its nature. So that is a property of hydrogen, right? It's flammable. We can take another element with another property and would say because of that property it's going to behave in a certain way. So that's what nature of reactants is. And finally we get to surface area. Now what is surface area talking about? Alright, let's say you have a solution, right? Here is a solution, right? And you want to react it with some chemical that is solid, right? So you submerge the chemical into the liquid. So it's a solid, and then it starts to react. Right, so this reaction takes 5 minutes. Right, but what if we take the solid, we break it up into various pieces. So we take the same solid, we don't change the size of the solid. We take the solid, we break it up into various pieces. Right, so now instead of the reaction happening in one place, it's happening in multiple places at the same time. So this will naturally speed up the reaction. So now the reaction might take 3 minutes. And so what did we do? We just increased the surface area. It's like a page, right? An A4 page, right? This has a certain surface area. Let's say 5 centimeters squared, right? But if you take that page and fold it up and make it a ball, it will decrease the surface area. Now it will have maybe 2 centimeters squared. So this is exactly what we're doing here. And let's say we even break it further down and we turn it into a powder. And we submerge it into the liquid. Now the reaction is happening everywhere throughout the liquid instead of happening in one place. This will also speed up the reaction. Now it's going to take place in 1 minute. So that's what surface area means. Surface area means you take something that is a solid, right? You take something that's a solid. But surface area doesn't only refer to solids, but we mostly talk about it with solids because it's most important with solids. We take a solid and we break it up into more pieces, or we expose more surface area like that, so more reactions can occur instead of having it small like that, such that the reaction will only happen on a small surface. So this is what we're dealing with in terms of surface area. So now what I'm going to do is I'm going to explain why temperature affects the rate of reaction in terms of collision theory. Okay? So let's do that. Okay. All right. Okay. So temperature. Okay. How would collision theory explain the fact that temperature affects the rate of reaction? So we first have to discuss what temperature is. So temperature is the average kinetic energy of it's the average kinetic energy of the molecules of an object. Right? So any object, since we're doing chemistry, solution, right? Since we're doing chemistry. So literally, average kinetic energy. Now what we know about kinetic energy, so what it's basically saying, when you measure temperature, you are measuring the speed you are measuring the speed of the molecules inside the solution. So it's the average speed of all the molecules inside the solution. So when you heat something up, when you add energy to it, what happens is that you increase the speed, the average kinetic energy of the molecules in the object or solution. Then that causes them to move faster, and that will increase the temperature of the solution, right? So, how does collision theory explain the increase and decrease in temperature affecting rates of reactions, since we understand temperature? Well, remember, collision theory says two things. In order for a reaction to occur, one, we need them to collide, so we need molecules or atoms to collide. And secondly, they need to collide at specific energies, right? They need to collide at specific energies, right? But here's the important thing, right, that collision theory says. So let's make a side note. Collision theory, again, can quickly make a side note. So collision theory says not all collisions form bonds / cause reactions, right? So they can collide, so cause reactions, okay? So not all collisions form bonds / cause reactions. What does this mean? So it means that if we have two atoms that have collided, right, it doesn't mean that they will form a bond. They could collide, but not collide at the right energy. So this will not be an effective collision. It would be an ineffective collision. Now, when two molecules or atoms collide and they form a bond or cause a reaction, we call that an effective collision, right? Effective collision, right? So this effective collision is when molecule or atoms collide, and then that collision leads to a bond or a chemical reaction, right? That means that that collision was effective. Okay? So that's a little side note that you should take about collision theory. But let's get back to the temperature. Okay. So temperature. So let's say we have a certain solution. Again, let's have another solution here. And there's a chemical reaction occurring. All right. So it's at a specific temperature. Let's say it's at 5 degrees Celsius. Right. And at 5 degrees Celsius, this reaction, this rate of reaction takes 6 minutes. Well, what if we increase the temperature of the solution, of the reaction? All right. Let's increase the temperature of this reaction. So we make it 10 degrees by adding heat, right? You can add heat to the solution. Same solution. Now we observe that the reaction takes place in 3 minutes. Okay, so what happened? So how do we explain this? Right? So this is what collision theory explains. We changed the temperature, it affected the rate of reaction. So what's happening? So one, what is happening? The rate of reaction has increased. Why has it increased? Because the molecules of solution move faster when the temperature increases. Right? So molecules of solution move faster when temperature increasing. Okay, why is this important? This is important because this means the molecules will collide more often. So when you increase the speed of these molecules, so they're moving at a particular speed at 5 degrees Celsius, but now when you increase the temperature, remember it's the average kinetic energy, increasing the average kinetic energy, meaning the molecules move faster than before, meaning there's a greater chance of them colliding, right? So this is why this affects the rate of reaction. Remember, it's collision and its specific energy. So one, you increase the energy of the solution. Number two, you increase the kinetic energy, meaning that they move faster. If they move faster, then it means they can collide more often. And the more often they collide, right there, the more often molecules collide, the more, okay, let's not use more, the greater, there you go, the greater the chances of effective collisions. Okay? So the faster they move, the faster these molecules move, the greater the chance of collisions, right? But not all collisions will lead to bonds or reactions. So the more often they collide, you need to specify saying the greater the chances of effective collision. So you see how collision theory is explaining why these particular factors affect the rate of reaction. So this is basically it with temperature. Increase the temperature of a solution, and the temperature of a solution is the average kinetic energy, and we all know kinetic energy is the energy of motion. So these particles are moving faster and faster, meaning that they'll collide more often, meaning that there are greater chances of effective collisions when you increase the temperature of a solution. All right, so now we can move to another factor, okay? Let's move to another factor. Okay. Now let us move to surface area. Okay? Let's take surface area. We're not moving in order. Surface area. So how does collision theory explain the effect of the change of surface area on the rates of reaction? Okay, so again, let's make an example of a solid, right, submerged in a liquid. Okay, then we have the same solution, but what we do is we break the solid into smaller pieces. So when you break the solution into smaller pieces, you are increasing the surface area, right? So remember, we have a solution, right? And we have a solid, and it's in the solution. So the reaction is happening on the surface of the solid, right? So when you break the solid up into smaller pieces, what you're doing is you're increasing the surface area. What does that mean? It means, so the reaction is not only happening here, but it's also happening there, it's also happening there, and there. Right? So what does this mean in terms of collision theory? In collision theory, it means, so, increasing surface area means one increases the likelihood of an effective collision. Okay? Why are you doing that? It's because initially we had a solid, right? So that means the reaction is happening around the surface of the solid, right? Or we can even call it, or we can even do it like this. So it's happening around there, and it's happening on there, right? When you break the solid up into multiple pieces, let's break it up into 1, 2, 3 pieces. So the reaction is not concentrated at one point. The reaction is happening there. It's happening there. It's happening there. All around there. All around there. So you can easily see that there's more activity. So there are more collisions, right? So more particles of the solution are colliding with the solid, right? As you can see, there are more particles there, and there than there are there in this particular solid. So we increase the surface area of a solid, we increase the amount of possible collisions, right? So there are more collisions there. When you combine these collisions and you compare them to the collisions at this one spot, you will see that there are a higher number of collisions on this side than there are on this side. Now remember, this here, we're not increasing the size of the solid, right? We're just taking the solid and we're breaking it up to smaller pieces, right? And if we continue to further break it down into even smaller pieces, now let's say this is the same solid, this is the solution. The same solid, this is the solution. Now, this solid is almost a powder. So that means there are collisions happening all around these points. Collisions with the solution, collisions. At each and every point, there are more collisions everywhere. So you can see, compare the amount of collisions here, and compare them there, and compare them there. You can see the amount of collisions are increasing towards that side, right? Because you are taking solid, you're breaking it up into pieces, meaning that you allow for more of the particles of the solid and the particles of the liquid to interact. That means you increase the collisions. That means if you increase the collisions, you increase the amount of potential effective collisions, right? Excuse me. You increase the amount of effective collisions. Now, another side note, again, side note time, collision theory. its effective collisions. So I'm going to keep reminding you, effective collisions, and 2 is energy. That's the specific energy. So it's a specific energy. Oh, and then one more. This is called orientation. Orientation of molecules. So what does orientation mean? Let me quickly explain orientation. What orientation means is, let's take water again. Let's take water, we have there, we have hydrogen, and then here we have a big oxygen molecule, right? So if you check the polarity, so we expect you to know what polarity is, right? So if you check the polarity, it means basically the distribution of charge around the molecule. We'd find that this side is more positive and this side of the molecule is a bit more negative, because there are bonds there with hydrogen and the hydrogen there, and here there are effectively no bonds. So this side is more positive and this side is more negative. Now when molecules collide, let's say we're colliding water molecules. If they collide like this, we have the oxygen there, we have the hydrogen there. So this side is also negative, this side is also positive. Do you see there? Remember, like charges, they repel each other. So like charges repel each other. So we're talking about the intermolecular forces between the molecules. So they repel each other, but if it now collides like this, if it now collides like that, okay, positive, 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 then the negatives there, and then you see the like charges attract. Okay, so the like charges attract, meaning here you will have an effective collision. So that's what orientation means. Orientation is how, which way the molecule is looking when they're colliding. So 3 things: effective collisions, energy, they must collide at a specific energy, and here they must collide at a specific orientation. Okay? So they must collide at a specific orientation. Now let's talk about this specific energy. It has a particular name. It has a name that they call it. This is called activation energy. Right? So this is called activation energy. So what is activation energy? Activation energy is the minimum amount of energy required for chemical bond to occur. So specific reactions happen at specific energies, right? So it needs to be at activation energy. And if the reaction is below activation energy, let's say we're talking about temperature. Let's say we're talking about temperature, right? Let's say we have a chemical reaction, A plus B, right? And this chemical reaction needs to happen at 5 degrees Celsius. And then you, not knowing that it has an activation energy of 5 degrees Celsius, let's say you expect A and B to react, but your chemical reaction is at 3 degrees Celsius. This means that this A plus B will react and form a product, right? And this will not form a product, because this is the activation energy it needs. It needs to be at least at 5 degrees Celsius and above in order for the reaction to occur. And if you have the same reactants but at a different energy, which is basically lower than the required activation energy, then the reaction is not going to happen. How does collision theory explain this? Collision theory explains this by saying that yes, A and B, the molecules of A and B collide, right? But remember what you need for, you need specific energy. Yes, they're colliding, but the collisions are not effective. The collisions are ineffective. In order for the collisions to be effective, it needs to be at this particular temperature, this particular energy. If it's at this particular energy, then when the molecules or the atoms of the reactants collide, they will form effective collisions, meaning it would lead to bonds or a chemical reaction. So that is called activation energy. Now there's often a confusion. There's activation energy, and then there is, okay, let's rub this off. There's activation energy, and then there's activated complex. So what's the difference between activation energy and activated complex? Well, activated complex is defined like this. It's short-term, high energy state during chemical reaction that can form products or reactants. So what does this mean? Okay, so you're having a chemical reaction, right? You're having a chemical reaction. So you have A, whatever A is, plus B, right? Activated complex, they say it's short term and it's high energy. So why is it short term and why is it high energy? The reason it's short term is because activated complex is actually, okay, we have here, let's say reactants. You can say reactants or reagents, it's the same thing. And you have a product. Okay, so you get your reactants, they react and then they form a product. So where does activated complex come in? Activated complex comes in right in between the reactants and the product. It's the stage of the reaction where it's not yet reactants and it's not yet products. So it's basically it's exactly the time when there are the most collisions, right? When there are the most collisions. So it's basically when the molecules are still colliding. So the molecules are colliding like that, right? And this is why it's high energy. It's because the molecules are colliding and they're still reactants and they're still product, but they are just about to collide or at the point of collision. And that's why it's high energy. That's why it's high energy. It's because of all these collisions happening simultaneously at the same time. So they're colliding, everything's colliding, so that means it's high energy. Why is it short term? It's because if two molecules collide, it's going to depend. Are they colliding at the right energy? If they're not colliding at the same energy, it's going to go back and form reactants. So that means the collision is going to be ineffective, right? So they're colliding, high energy collisions. Now, If they collide and they form a chemical bond, then they're going to start forming products. So that's why it's short term. So it's right there in that moment when the molecules are colliding. After that is depending on the energy. If the energy of the collisions is sufficient, then it's going to form products. That means it's an effective collision. If the collision of these atoms or molecules are not sufficient, then they're going to form reactants. Right? Why did I say reactions there? Reactants. Right? So they're colliding, but poof, they don't bond. And then they form back the reactants. And then if they collide and have sufficient energy, they form products. So this is basically activated complex. And this is activation energy. So activation energy is the minimum energy required for a reaction to happen. So it needs to happen at 5 degrees, 10 degrees, 25 degrees, 100 degrees. So then if you're going to make that chemical reaction, it needs to be at 100 degrees or it won't happen. Activated complex is describing the middle point between reactants and products when they are colliding. It's the highest energy point, right? And when they are colliding, it depends on the energy of the solution or the chemical reaction. And if the energy is not sufficient, it's going to form reactants. Simply going to go back to forming reactants. And if the energy of the solution is sufficient, then it is going to form the products. Okay, so please remember that, distinguish between these two, activated complex and activation energy. They're not the same thing, and you need to understand how to differentiate between the two. Okay guys, so this is where we conclude our lesson today, right? There will be a following part, which will be a part 2, which will further explain the things that I left out today, right? Let's do a quick recap of what we did today. Today, we did collision theory. We explained what collision theory is and how it explains bonds and chemical reactions between atoms and molecules, right? Secondly, what did we do? We did the factors that influence rate of reactions. Okay, we discussed them. There are about 5 to 6 factors. So we have concentration, we have temperature, we have pressure, we have nature of reactants, we have surface area, right? So these are the factors that we did today. And also, you must be able to explain these factors in terms of collision theory, right? So you must understand in terms of collision theory why these factors that I just mentioned affect the rate of reactions, right? Okay, and what we will do next week we'll simply finish off, because I think I did 3 factors and I explained them in terms of collision theory. Next week we're going to do rate of reaction graphs. Rate of reaction graphs. Start with the basic one, which is that, right? You have time over there. You have reactants. And then you have products, right? And then the reactants go down, and then the products go up. So next week, what I'm going to do, or part 2, what I'm going to do is I'm going to finish off explaining the factors in terms of collision theory, and then we're going to start explaining the graphs. Why do the products increase when the reactants decrease? What happens when there's a straight line like that? What happens if the graph continues? What happens if this goes up and it comes down? These graphs look very intimidating and very complicated, but I promise these are very simple graphs, and in part 2 we are going to be tackling this. So thank you.